Hello, everybody, and welcome to this epic webinar on biosensors for virus detection. My name is Ana González. I am R&D Manager at EPIC, the European Photonics Industry Consortium. And well, I am not alone here. I am with the top specialists in Europe to talk about the potential of photonic biosensors based on integrated circuits for virus detection. So, first of all, I would like to introduce to Inigo Artundo, CEO at the BLC Photonics, a design house for photonic integrated circuits technologies. Hello, Inigo. How things are going in Valencia?
Hello, Anna. We are doing fine. Hello, everyone.
So maybe you would like to introduce yourself and what your company, BLC Photonics, is doing?
Sure, absolutely. So we are a company based in Valencia, in Spain, and we work on the field of integrated optics and photonics and providing all kinds of services to help people develop their solutions based on photonic integrated circuits. So, and I will be representing Pix for Life consortium, and you will see in a few minutes what we have to tell about that.
Very good. Thank you, Inigo. And now I would like to introduce, I am also here with Arne Leinse, CEO from LioniX International, a vertical manufacture company for designing, from design to large volume manufacturing of photonic integrated circuits based products. So Arne, how are you? Everything fine in the Netherlands?
Everything fine in the Netherlands, Anna. Thank you for the introduction. So I don't have to explain a lot about LioniX anymore. Indeed, a vertically integrated foundry specialized in silicon nitride waveguide technology, involved also in the Pixapp and Pix for Life project that Inigo will talk about. So I'm looking forward to the webinar.
Okay, very good. Thank you for this introduction. And well, last but not least, Padraic Morrissey, Technology Manager from Pixapp pilot line. How are you, Padraic? Can you introduce yourself and yes, what is Tyndall Institute and Pixapp doing?
Okay. Hi, Anna. And yeah, everything's good here in Ireland. So as Anna said, I'm Padraic Morrissey. I'm Technology Manager of the Pixapp pilot line and also Technology Manager of the Photonic Packaging Group in Tyndall. So Pixapp is the world's first open access packaging pilot line. So we provide users with a kind of a single point of contact for photonic packaging solutions right across Europe and across the world.
Okay, so thank you very much for these introductions and for being willing to be here today to talk about the new developments on biosensors for virus detection. First of all, I would like to talk a little bit about EPIC. EPIC is the Industrial Association of Companies working on photonics, European companies. Our goal is to keep a strong industry, so for this we organize meetings, we elaborate market reports, and also we help our members to fill job position, contact with investors. So as you can see here, our companies cover the entire supply chain, from design, software, manufacturing, to automation, everything. And also these companies are active in many markets, such as healthcare, optical communications, of course, environmental, everything, okay? So EPIC also collaborates with the European Commission in promoting, in making sure that all our companies in our network have access and know about the pilot lines in photonics. The pilot lines in photonics is an initiative of the European Commission in partnership with Photonics 21, and we have 4 different pilot lines: Pix for Life, for silicon nitride technologies, chips, visible light, healthcare technologies, MIRFAB for prototyping of chemical sensors, working with mid-infrared technologies, and JPIC's pilot line for manufacturing large volumes of indium phosphide chips, and finally Pixapp, that is for the packaging and assembly of these photonic integrated circuits. So yes, we have the industry is mature enough and our supply chain is very strong. So working in this pilot line, we have foundries, we have all kind of companies for mid-infrared technologies, software providers, design houses, companies able to do all types of packaging. So we have a complete story. We have the pilot lines that can produce the chips. Pix for Life, JPix, MIRFAB, and then we have Pixapp for going to large volume for the packaging of these optical modules. And this is my last slide. Well, at EPIC, we are trying to adapt to these crazy times. So for that, we have organized different online events. So here you can have some of them. And if you are interested in participating, you are an EPIC member and you are interested, you can go to our website and register for them. So yes, that was my last slide. So now I would like to give the floor or the screen to Inigo, Artundo. So Inigo, if you want, you can start.
Yeah, thank you very much, Anna. So I'll be discussing in this webinar about the silicon nitride pilot line Pix for Life. I'll be introducing that in a second, and how this could be applied for biosensors, especially for virus detection. We only have so much time, so I won't get into many technical details. Also, there will be a follow-up presentation by my colleague Arne from LioniX, entering into a bit more details on one of the fabrication platforms in Pix for Life. So I try to give this webinar in a more general way for people that maybe are not familiar with photonic integrated circuits, and also try to give you an overview of what is available. If you have any questions, please, there is a way on the teleconferencing system where you can write them. So let me start by saying that that Pix for Life is a European pilot line. Pilot line is a terminology that is used here in Europe to mean that is providing services, open access services, especially on the manufacturing, but everything around manufacturing, that allow you to move from prototyping to large volume production of photonic integrated circuits. And especially in this case, in Pix for Life, we are targeting visible wavelength ranges. So this means from 400 to 850 nanometers, and using for that a silicon nitride material platform. So first of all, let me start by explaining what is a photonic integrated circuit, because many people are familiar with integrated circuits, usually electronic integrated circuits, electronic microchips. Well, a photonic integrated circuit is equivalent of that, but instead of using electricity, electrons, it's using photons. It's actually using laser light to perform different functionalities, right? So this may be injecting light, extracting light, dividing light in different channels, changing the frequencies or wavelengths of the light, etc. This has many applications, but here you can see, for example, a very classical example of a laser combination system where we are combining different light sources. And traditionally, you would do that by combining different discrete components, as you can see on the left setup, in the left picture setup. And this is quite bulky. It requires very tight alignment of the different components, etc. So this nowadays could be integrated into a microchip. And you can see here that this is a small microchip on a wafer level. And this photonic integration technology allows you to miniaturize this complete optical system into a microchip. In principle, the concept is the same as with electronic integration. So what we can see is that photonic integrated circuits, and in general, integrated circuits, present different advantages to miniaturize optical systems. Obviously, the first one is that it reduces the volume and the weight of the system. This is pretty obvious, and this might be critical, for example, in medical instrumentation when you need to have a handheld device instead of a big rack to move around in a hospital. It's much more convenient, right, for operation. Obviously, it also enables to have very complex systems. Needless to say, for example, in electronics, you have electronic circuits that have millions of components inside. Well, in photonics, we are not at that level yet, but this means that we can actually combine hundreds, or in some cases even thousands, of optical components into a single microchip. And this opens up the possibilities to develop and produce very complex optical systems into a die size. One important advantage as well is you don't have a complete optical system to be stabilized in terms of mechanical and thermal stability, which is usually very complex because it means that you have to align lasers with photodetectors and optical fibers and prisms and lenses, etc. You only have one chip. So this improves very much the whole stability of the system. And because this can be produced using lithographic techniques in a wafer level, you can scale up the production from hundreds to thousands to millions, if needed, of units, same way as in electronics. And also it simplifies very much the optical assembly and packaging, because it's only one chip that you need to assemble, and obviously reduce the cost if you are able to scale up in volumes. So there are many advantages, as you can see. But specifically for this kind of applications that we are discussing today, we are looking into life sciences, and specifically on the visible wavelengths. There are many biological processes that happen in the visible wavelength range, and there are many applications here, from diagnostics, label-free sensing, the kind of ELISA testings that you could do on a chip, lab-on-a-chip instrumentation, for example, when you are combining these kind of photonic microchips with microfluidic channels, to be able to measure analyte concentration, to control chemical reactions and things like that. People are also applying that to DNA sequencing, optogenetics, also in medical instrumentation like microscopy, like flow cytometry. We'll see an example of that later on, and optical coherence tomography, spectroscopy, etc. So there are plenty of applications where people are looking into these photonic circuits for life sciences. Looking a bit more in detail on virus detection, well, it's based on a few basic principles, right? So whenever we are infected by a disease, and we are not looking here into only viruses, but also maybe bacteria, antibodies are generated in our bodies, right? And they are into our bloodstream. And these antibodies attach selectively to a specific part of the intruder, and this specific part is actually depending on the intruder, so it's not always the same. And this is called the antigen, okay? It's kind of a label for the immune system to attack. Obviously, if you would need to diagnose an infection, you will need to also have a measurement of the concentration of these antibodies. And this is very low if you compare it to other biomolecules that are in the bloodstream, okay? So it requires also a way of having this transducer, photonic transducer in our case, that is able to fix the antigen into a biosensor surface. For example, in the example that you can see here below on the slide, in this case it's a microring that has some antigens on the surface, and then they attach to the antibodies, only to the specific antibodies that you want to measure. And this way you can select the measurement of the antibody that you require with very high selectivity, okay? There are different structures that you could use, photonic structures that you could use to fix these antigens and these antibodies. In this case, as I say, this is a waveguide in a microring configuration, but there are many others. So I'll show you a few examples of actual things that have been developed in R&D using, in our case, silicon nitride as a material platform, because as you may know, in electronic integration, the most common material platform is silicon. But in photonics, there are different material platforms. And we are only looking here at silicon nitride because it's actually transparent in the visible wavelength ranges, which is actually our wavelength of interest. So here you can see a sensor that is used to detect tuberculosis for point-of-care applications. And as you can see, the chip is in the middle of a microfluidic cartridge. This chip is coming from a wafer, and you can see the immunoassay here by detecting the antigens and the antibody. And you can see this visible light being shined into the chip, and by doing this, measuring the concentration of the antigens and the antibodies. Sorry, let me explain that this was also part of the results of a previous European project. It's called the Pocket Project. You see the reference here below on the picture. You can check on their website. Another research and development example is something that is actually happening in the Pix4Life pilot line project as part of the demonstrators we have with Bosch. And it's a multi-sensor, a gas and bio multi-sensor. And that's interesting because you can combine these not only to measure molecules, but also to measure all kinds of parameters, like, for example, temperature as well, because the waveguide, the transmission of light in the waveguides is also dependent on the temperature. So it could be used also as a temperature sensor or as a gas sensor as well. And this allows to have in the same microchip different sensors for different things, different viruses, different bacteria. Again, another demonstrator that we have in the Pix4Life pilot line project is flow cytometer that is able to, well, it's actually this kind of cytometer systems are used to do cell counting or sorting, to detect biomarkers and also do protein engineering. And for doing that, you need to shine the flow of cells or molecules with light coming from different lasers, each of laser with different wavelength. So eventually you need a wavelength combiner. And this, as I say, are usually implemented, as you can see in the image here, with prisms. And this is very bulky and difficult to align. So if you could do that with a microchip, that would be much simpler. And this is actually what we have demonstrated in the pilot line, together with some of our partners, Miltenyi Biotech and Toptica. That's not the only thing. There are also commercial examples of these kind of applications. So you can see here a couple of companies working on these topics. Biosensors, it's a company here in Valencia working on silicon nitride photonic sensing systems. And they have been actually trying their system in swine viral diseases. They have demonstrated already that. There is a paper on that. And there is also a company in the States, it's called Genelite, who actually are working, well, they have been using not silicon nitride, but silicon photonics, also photonic integrated circuits for biosensing. And specifically, they are developing recently, as you can see on their website also, a specific system, the Maverick system for this COVID-19 disease, right? So this is actually a market reality. It's not only R&D, but there is actually people working on products in the market on this. So, and this is what Pix4Life is supporting you and being able to support all these applications. Let me go back to this slide because it means that we are actually offering an open access manufacturing platform to develop this kind of photonic circuits, this specific kind of photonic circuits, okay? So what does this mean? It means that we can provide the complete supply chain, okay? Starting with the initial consultancy to support you on how to define an optical system to be integrated into a photonic microchip. Obviously, not all of you will be experts on photonic integration technology, so this will be needed also in order to evaluate the limitations, the trade-offs, and to specify the whole system. Then helping you with the design of the microchip. Some of you might not be able to do a photonic circuit layout of a chip, so we have services to help you design on that, or we can design that for you. Obviously, the manufacturing, which is the key part of having access to, in our case, 2 different fabrication platforms. As I said, in silicon nitride material substrate. I will describe them in a minute. And then after the chips or the wafers are fabricated, being able to test them, to characterize these chips and put them into a package. This is very important because a package means that you can actually take that out of the lab and put it into a module or an equipment and have it ready to be used, right? So all these services are offered through our website. You can see the address here, pix4life.eu. If you enter there, there is a lot of information you can see. And it's not only about prototyping or demonstrating an R&D concept, but also it's taking that into pilot production and eventually into volume production, all in the same ecosystem without needing to move to a different place, right? This allows you also to have a very easy way of accessing these platforms with a library of photonic building blocks or components that you can just plug and play into your layout of your circuit. It also means that you can integrate active devices like lasers, devices like photodetectors, waveguide sensors or waveguide interferometers, like micro rings, like Mach-Zehnder interferometers, well, all these kind of structures that you could be using. And also we collaborate very closely with Pixapp, which is a packaging pilot line that Padraic will be introducing in the third call. So let me give you a little bit of information also on the 2 fabrication platforms that are available in Pix4Life. The first one is at IMEC. It's called the BioPix platform. IMEC is a large research institute in Belgium. And they have a silicon nitride fabrication process using PECVD. It's actually a 200 millimeters wafer line, pilot line. They do processing directly on CMOS. It means that the resulting chips are very compact, and they have 2 different platforms optimized for different wavelength ranges. So the 150 nanometers thickness of the nitride platform for operation at 400 to 700 nanometers wavelengths, so the visible wavelength range. and a bit thicker platform, the 300 nanometers thick, for higher wavelengths, 700 to around 1,000 nanometers. And here you have the cross-section of the waveguides that you could be fabricating in this fabrication process. The next platform that will be introduced a bit more in detail by the next speaker, Arne, from LioniX, is the triplex platform. It's a well-matured platform that has been used for decades already, and is based on LPCVD. It's a very high-quality silicon nitride, stoichiometric silicon nitride deposition. It presents excellent transparency in the visible wavelength range, which means that you have very low propagation losses. There are also available extra processes, extra modules that you could implement on top of the basic fabrication process, like, for example, having piezoelectric material for high-speed modulators, or glass processing. You could also have openings on top of the waveguides, things like that. And again, they have two available platforms, again, for the visible wavelength range, 400 to 700 nanometers, and then another one slightly different for higher wavelengths, around 850 nanometers, okay? So I won't get into many details here because Arne will explain a bit more later. So how to access these fabrication capabilities? So both foundries, both IMEC and LioniX, run what we call multi-project wafers, MPWs. They are also referred in electronics as shuttle wafers or shuttle runs. And the idea here is that instead of customers needing to buy or book a whole wafer to prototype or produce their designs, they just book a part of that. So you actually share the cost of fabricating such a wafer among different users. So you have only access to a small part of the wafer or a small part of the reticle at a reduced cost. So this lowers very much the barriers for getting introduced in the technology and allows for a very easy and low-cost access. There are many MPW runs scheduled over the year. You have the schedule in our website for both IMEC and the LioniX platform. And both platforms also have full design and test support through the pilot line, through Pix for Life, okay? So that's everything I wanted to introduce today. There are many companies involved here, not only the service providers like the foundries, the softwares that allow for this, and the design houses like VLC Photonics, but also people that are actually using these platforms like Bosch, like Miltenyi, like Medlumix. So this is actually a reality. The project is about to be finished after 4 years. And it's up and running. It will be up and running after the project, the funding is finished. And we are really open to help you prototyping and starting all your developments using photonic integrated circuits for virus detection or whatever other healthcare application you may think of. So thanks a lot. And if you have any questions, I'll be happy to answer.
Thank you very much, Inigo. Very nice presentation, very interesting services. And well, I have a question. I mean, BLC Photonics is a design house. So when imagine that I am a company and I want to produce my own sensor, but I don't have idea how to do it. What are the key points to take into account when designing a PIC for biosensing?
Yeah, so that's a good question. So we have many cases like that. So people that are experts in biosensing or biophotonics, but they don't really have the expertise on how to actually develop a photonic integrated circuit. So that's where we come in. As a design house, we understand all the different material platforms, all the different foundries, the capabilities for each foundry, and we try to translate what are your needs in terms of the optical system or application needs into a photonic integrated circuit. And once this is clear, then you can either try to do the design of the circuit yourself, and also we can support you on doing the design for you, and eventually also testing the design. So we act many times as an interface or a bridge between the end users, so the application, and the more technological partners like the foundries and the packagers.
Okay, thank you. We have a question from the audience, from an EPIC member, from Nanoscribe, Joel Smolensky. He is asking, can there be done PCR for virus detection with PIC sensors? I guess he would like to know if we can make some kind of PCR, right, on top of the photonic integrated circuits.
Yeah, so I'm really not an expert on PCR. I'm an expert more on photonic integrated circuits. But what I can tell you is that companies like Lumensia or Genelite are actually doing this kind of quick tests for these virus detection systems. And they are doing that in a multiplexed way and being able to have results in a matter of minutes, like 10, 15 minutes as far as I know. So in principle, I assume yes. This is possible.
Okay, and we have another question from Antonio Raspa from another EPIC company, Quanta System. What about the support? I mean, in order to get the biological receptor, what is the support that Pix for Life is giving to the companies?
So I guess he refers to the biofunctionalisation of the chip. Yes. Is that right? So that is very, very dependent on the end application. So we cannot obviously have all the different functionalizations for all the different applications. But what we can do at Pix for Life, and this is something we have been doing in the past, is also actually forward the end users to the external partners that we know that are able to do these kind of things and have expertise on that. So it's not something that we do in the consortium because it's not actually photonic related. It's more like biochemical related, but we have partners, all of us, that could help on that respect, yes.
Okay, also Padraic is going to say something with the, because the biofunctionalisation is also one of the building blocks in the Pixapp pilot line. So. Okay. Another question that we got from the audience. So he is from Hani Gansby from the Huston University. So thanks for your interesting presentation. Have you tried this silicon nitride for detection of viruses before? If so, which virus you detected? Thanks.
So not ourselves, but this has been tried actually. And as you can see on the previous slides that I showed, let me go back to this slide. So actually, as you can see here, Lumensia, this company actually tried that for swine viral diseases. So it has been tried already in silicon nitride, actually, using microring resonators. And there are other references you can search online. Yes, it has been tried out. Yes.
Yes, it's possible. Yes, I agree. Okay, so yes, so I think we are okay. So if you still have more questions, you can still write the questions, and Inigo will answer. In the meantime, so we will take them again at the end of the discussion. Yes, at the end of the webinar. Okay, so then I would like to give the floor to our next speaker, so Arne from LioniX. If you are ready, the screen or the floor is yours.
Thank you very much for the introduction. Yes, I'm ready. Let me see whether the slide deck works. If I'm correct, you should see the slide move to the next one. Thanks, Inigo, for already presenting our technology and for paving the way already for the fact that integrated photonics is not a sensor by itself. It's not a product already. So what I want to talk in the next 15 minutes about is collaboration between 3 companies and showing an example of one of the technologies in Pix for Life. It's a collaboration with LioniX, Curin, and Surfix, showing the different building blocks you need to build these kind of modules for any kind of biosensing, but also virus detection. Because if you look at the chip itself, if you look at a biophotonic sensor, that starts with a chip. It starts with surface coating of your system, the biofunctionalisation, and afterwards also the protocols, the modules to read out the proper concentrations and proper selectivity from your sensor. As said, we are vertically integrated foundry specialized in integrated optics. So our core technology is in the chip production. I'll first present that platform and then show you how we built that into a module together with the other companies, showing you some examples of the measurements. So the waveguide platform, which Inigo already showed, we call that triplex, and that's based, the name resembles, comes from 3 layers, nitride, oxide, nitride. It's based on indeed low pressure chemical vapor deposition silicon nitride, which gives always the highest quality silicon nitride. And a unique selling point actually of silicon nitride is twofold. One is that it has low optical attenuation and the fact that you can match your mode profiles, you can play with your mode profile, you can play with your evanescent field in your sensor, perfect for sensors that you can maximize it for surface sensitivity or for bulk sensitivity in your sensor. And very importantly also for sensors, you see the picture in the lower right, it's transparent also in a visible light. And that particularly for a lot of fluorescent excitation, visible light is very suitable. I'll show you the sensing platform we have with our present today works at 850 nanometers. I'll also explain you the reason why in one of the later slides. But first, show you the 3 types of sensing that we can do with optofluidic sensor. In an optofluidic sensor, we got a waveguide, in this case, turning coming from left to right, and you open up the top cladding there to have some kind of sensing window where you can either have a fluid or a liquid or a gas in there. And the easiest sensing there, of course, is look at absorption. Look at what happens, how much light do I get out, and what specific absorption peaks are there in the system. The second one, which is very often used, and therefore also the visible light is very convenient, is that you use that fluorescence excitation. So we send in one wavelength, we excite some biomarker that starts to show fluorescent behavior. We collect that light again in the same waveguide, and that light is detected. You can actually, once you're on chip, that's a nice thing. The world is your oyster. You can easily filter out components, things which are normally difficult to do in bulk photonics. In an integrated photonic device, you can easily add these kind of filters and switches and power taps, etc. The most interesting actually for virus detection, because the downside of the fluorescent excitation is that you have to prep your sample. Not every virus, not every sample you want to measure is showing fluorescence. But the moment you can do something label-free, so we put the selectivity on the chip and just measure whether that certain component, either a cancer cell or a virus, is present in your sample. That's the main focus of these kind of detection systems. We talk about label-free sensing. And for those, you want to just look at a refractive index change or a change of something happening on your interface. The basic building block for that actually is what you see in the picture here. It's a ring resonator, and Inigo also showed them already in different platforms, but it's just we always call it the workhorse or the transistor of photonics. It's something which easily shows a change in refractive index, a change in resonance condition. Because what happens is you couple in light, and for certain resonance conditions, the ring gets in resonance, and any small disturbance in that ring will move the spectrum of that ring give it a small change of resonance condition. The big benefit of these rings is that they're very small. You see in the middle picture an array of these in the fluidic channel. You can put multiple in those and measure the same plug. You measure the same small analyte into a microfluidic chip. Because a sensor is not only a photonic integrated circuit, you also need a chip around it. You need a chip to prep the sample. You need a chip to flow the sample over your chip. But instead of instead of a ring resonator, actually, there's one better building block. And you see the ring resonator here at the top, and you see the spectral response also of a typical ring resonator. And actually, the more sensitive building block is what you see in the picture below. And that's an asymmetric Mach-Zehnder. It's a Mach-Zehnder interferometer, where your gut feeling would be, if you look at these two spectra, typically these rings have very steep peaks, which are easy to detect indeed when you detect a shift. The gut feeling first says the top picture is easier to detect a resonance shift. So that one must be much more sensitive. I'll show you actually in the next slide that that's not the case. So with an asymmetric Mach-Zehnder, you can generate a much more sensitive sensor, and therefore increase sensitivity in detecting really individual biomarkers or individual cells that you capture on your top of your surface. Because if you look at the top chip, and you see a chip here with Mach-Zehnders and with ring resonators, if you look at the top of these, nice thing of being on a chip is that you can have sensors with sensing windows, and in that same part you can have reference ring resonators or reference Mach-Zehnders. So the nice thing is that temperature stabilization, any variations of the environment, they're all easily taken out because you have your reference on the same measurement chip, and you only look at the difference between your reference and your chip or your sensor in which you put your analyte. But if you look at a Mach-Zehnder, and if you look at the sensitivity of such a component, it's the only formula I have in my slides. But if you look at the sensitivity of these kind of components, what you see there is that the sensitivity depends on the free spectral range of your ring, but also on the path length that you can measure. And that's the downside of a ring resonator. Because if I increase in a ring resonator the ring length of my sensor, my free spectral range goes down. So these two compensate each other. In a Mach-Zehnder, however, if I use an asymmetric Mach-Zehnder, I can vary the sensing length and the free spectral range of that Mach-Zehnder independently. And therefore, all of a sudden, I have two parameters that I can play with by increasing sensitivity. And in the next two pictures, you see an example of this. This is a measurement we did on one of the samples where we had ring resonators. And the samples are in the same chip, actually, the chip you see on the left. So we have ring resonators and Mach-Zehners, both with the same, flushed with the same sample. And the Mach-Zehners, in this case, had a 10 times increased sensitivity by design than the ring resonators. And that's the nice thing once you're on a chip environment. You're in a controlled environment, and you can very accurately read out the refractive index change. However, the refractive index change is not what's making your sensor. Because what you see here in the picture, you see here that this is typically a chip. You have sensing windows. You have, in this case, up to 8 different sensors, which you can functionalize each of them with a different concentration or with a different biofunctionalisation. However, the selectivity only comes when you determine which analyte or which biomarker adheres to your surface. And the trick we have for that is actually, so this is on the right side, the chips are there, the platform is there, but the trick is actually developed not by us, because we can't do that. It's a surface modification done by Surfix. And what you typically see in these waveguides, in the sensing window, you see a picture here where the waveguide meanders around it. And if I would coat that with some kind of selective biochemistry, you see that in this case, the viruses or the markers I want to measure are in purple. You see that they can adhere everywhere. And with a loading of a waveguide of less than typically 1%, you see that all of a sudden, only 1 in 100 hits my waveguide. And that's all of a sudden giving me a very poor selectivity. More ideally, what I would like to have is this. And the nice thing is that you can do that trick by using the composition of nitride and oxide. And that's the benefit of being in a controlled environment of a chip. The moment you have 2 different materials, you can always also play with the chemistry of those. And by using the nitride, we can make sure that we first only make the nitride layer reactive or active by applying a chemistry which only adheres to silicon nitride. And we apply an anti-fouling layer to the rest of the surface, to the oxide surface, and then the functionalization is done. So the functionalization only adheres to the silicon nitride waveguide. And then all of a sudden, if you apply the materials you want to measure, they can only adhere to the waveguide. So all of a sudden, you increase your sensitivity not by making a smarter sensor, not by making a smarter photonic integrated circuit, but by making a smarter chemistry on top, or making it more selective. And that's actually the main message of, and I was happy that Inigo showed that same picture, or that same message. It's not about the chip, it's about the complete system, it's about everything around it. And if you measure with those after that, there's a typical measurement which we did on one of those samples. You see a ring resonator or Mach-Zehnder based sample here with 6 different measurements on there, or 6 different windows on there. 2 of them were coded to be responsive to one protein, the other 2 to another protein. And what was done here is on the same chip, we flushed over different concentrations. On the left side, you see that only the, in this case, the orange and the blue line pop up, so only sensor 2 and 4. The nice thing is that on the right picture, it's the same chip, just a different measurement in time. The different proteins were flushed over it in different concentrations, and the other ones were active and showed a really good selectivity. The platform is there, the chemistry is there, so now the next step, and that's where we closely collaborate with Kieran and Surfix, is that you do the same trick, but then make it susceptible to the virus. And you can do different options for that. You can either measure the RNA of the virus, or you can try to capture the whole virus in some kind of a membrane or ligand that is selective for just capturing that virus. The most promising one there would be the RNA detection, to be honest at this point. But that's the main step there is to develop the biochemistry to take that into account. So that's the next step also for COVID-19. We're aligning everything now to see how we can get that done in the near future. The devices are there. So the platform there you see in the lower right here, even an handheld version already, where we got light sources, detectors integrated that you can really, it becomes a disposable, where with a droplet of saliva, you can measure whether the virus is in somebody's saliva. So ideally, in the near future, you could do a 100% check when travelers come into the country with small chips and a handheld. I always compare to a glucose test. You apply a small droplet of saliva or blood, and you can detect whether somebody has a certain virus in the sample. And where do we stand? Where do you stand at this moment with biosensors for virus detection? Is that the PIC platforms are ready. The PIC platforms are there. The electronic readouts are there to test everything. There's lab-based systems, but they're there to already start testing immediately. The trick is the biochemistry. That is done for non-viruses, but what I was told by the people who do that biochemistry, the trick to make it into viruses is not rocket science, it's engineering to just match them to the right RNA types of the virus. And then in the future, it's also compatible for volume production by integrating light source and detectors on the chip. So in conclusion, a chip itself is not a platform. That's actually what would be my conclusion. And if we want to defeat this, if we want to do virus sensing as a consortium or as the ecosystem, we should make sure that the full supply chain is there and the full supply chain is aligned. And that's what's currently happening in the world also, that people start working with their own core capabilities. And by aligning everything like we've shown for the other measurements, you can also do the virus detection. Any questions so far?
Thank you very much. Very nice presentation, Arne. Okay, so I was wondering for the sensors that you are preparing to detect COVID-19, you have the 8 channels. So what are going to be useful for? For detecting maybe 8 different patients using the same chip, or like yes.
The current ones have 8 channels indeed, because you can detect multiple analytes on one chip. Ideally, what you see is that you measure multiple negatives, so to say, so that you always want to do a test and have also multiple positive measurements. So ideally, you select some control values on these ones. And with these 8s, I would say you could normally do 2 different analyte measurements. But you can expand this also to bigger matrices if you want.
Okay, and what about microfluidics? Because you also have to take into account that the sample, the patient sample, has to flow to the sensing area. How are you doing this?
Yeah, I didn't put that into this presentation. That depends on the application. We can also do it, or we collaborate also with other foundries who specialize in these kind of low-cost fluidics, for instance, because you can integrate these chips also in plastic microfluidics. However, the trick is in these kind of cheap sensors, not that you want to have an expensive lab on a chip system around it. You want something which is either capillary flowing over the chip, or where you can just apply a droplet to some kind of a beaker or some kind of capillary force sucked in, that it's then automatically added to the chip.
Okay, perfect. So now we got several questions. Let's go through them. Yes, from Antonio Raspa, Quanta System, sorry. The detectors from LioniX are single-use or can be reused?
In principle, in the lab, they can be reused. So what we do here in the lab with measurements is that you reflush them with so that you can get the analytes or the measurement surface clean again. Ideally, in a product for these kind of virus detections, it's a one-off. So what we do is we take in the light sources, in the fully integrated version is a VCSEL, basically an 850 nanometer VCSEL coming from the mouse industry. Those really cost cents. The same holds for detectors in that range. It's a nice thing of nitride, it's transparent in that range. So in the end, in the volume application, you throw away the sensor, including detector and light source. You can then rework that or recycle that, but the sensor will be single use then.
Okay, and what about the sensor surface? Can be regenerated and then we can use again the sensor? This is a question from Tarun Narayan from Tyndall National Institute.
In principle, you can. We also do that with some of our sensors if you want to test different kind of concentration or different kind of biochemistry. However, and I always, if I say this, I always get people asking me for very cheap wafers, but silicon nitride is not expensive. The nice thing is it's only glass. So ideally, what you have is you start with a clean surface every time and you make it a disposable where you have a known starting point from every time. You can clean it, it's just chemistry. The waveguides are nitride oxides are very resistant to all sorts of chemicals. But from a cost point of view, it's easier to just take a new chip.
Okay, next one. It is possible to measure concentrations. How it is calibrated? From Victor Brash, CSEM.
Yeah, that's possible. That's what you see in this picture, for instance. Where is it? This picture. Actually, what you see is the total amount of shift here represents concentration. So what you see on the left axis is the shift of your resonance condition. This shift actually means how many particles will bounce to the sensor. The slope of this gives you the concentration, because the higher the concentration, the quicker the total surface is filled with the parts you want to measure.
Okay, very good. Well, next question is more about packaging. So we are going to keep this question for next presentation. Also, we got another question that is better for the end. Do you think CVD diamond grown on silicon substrates can be an added value to this technology? Thomas O'Calci from CAT.
What material system? The line was a bit.
CVD diamond grown on silicon substrate.
I don't know, to be honest.
Maybe some waveguides with the new kind of waveguide technology with this.
Exactly, and that's why I'm not saying no. Right now, I see that the bottleneck in these kind of sensors is not in the chips anymore. The challenge now lies in the biochemistry and making that stable, reproducible. But what I've seen is the moment you start adding new components to the chip, it opens up new applications and new possibilities. So it could certainly be. I don't know.
Okay, we have more questions, but I am afraid we need to move forward. So, but well, now Arne will answer your questions, so we will come back to them later. Okay, so thank you very much, Arne. So now, next and last speaker, Padraic, if you want and you are ready, you can start.
Okay, hi Anna. So I think this should be a pretty logical follow-on talk from both Arne and Inigo. So I'm going to talk about how what Pixapp is doing to actually take the photonic ICs from Pix for Life, from LioniX, from other foundries, and actually how we're developing low-cost packaging solutions for them. So again, if you can see my slides, so on the general overview for my talk today, I'm going to give a quick motivation for why we need photonics packaging and integrated photonics. I think Arne and Inigo have already touched on that already. I'm going to talk about Pixapp, the world's first PIC packaging and assembly pilot line. And from there, going to move on to how we're developing packaging building blocks to create scalable photonic packaging. And finally, I'll end by talking about some of our work that we're doing currently on the packaging of optical biosensors, which could be used for virus detection as well. So again, I think as you saw in the previous two talks, so photonic integration allows us to integrate multiple photonic functions onto a single chip. And there's lots of great benefits to this in terms of compactness, it's cheaper to produce, increased functionality, lower power consumption, but there are some disadvantages. And one of those, I suppose, is really it's more costly to actually integrate them into larger systems because you need photonic packaging. So again, just as a quick kind of summary again, so photonic packaging, we take those photonic integrated circuits and we package them into compact electro-optical modules that are easy to use, easy to handle, and can be integrated into those larger systems or subsystems as required where they can actually be used. So this can be for the automotive industry, for telecommunications, or aerospace, or in light of the current events that's happening worldwide for medical applications like for virus detection or bacteria or medical sensing or imaging. Now, across the full PIC manufacturing supply chain, ideally what you'd like is equal and open access for all users to all the technologies required to actually make these photonic products. This includes how PICs are designed, how they're fabricated in foundries, how they're packaged, how you test them, and also how they're analyzed for reliability afterwards. And today I'm going to mainly talk about packaging. So packaging is probably one of the most inaccessible aspects of the whole PIC manufacturing supply chain, and it's also probably one of the most important, and that's primarily driven by the costs actually involved in packaging these photonic integrated circuits. So the time, effort, and cost associated with designing and manufacturing a PIC is quite high. However, when we consider the cost of an overall packaged device in an actual photonic product, it only accounts for about 20%. So more than 50% of the cost actually goes towards packaging and assembly, and over 80% goes towards packaging, assembly, and also testing. So to keep the cost of a photonic device low, you really need to keep the cost of the packaging as low as possible too. And there's several reasons why photonic packaging is so expensive. So there's operational challenges, including a very fragmented ecosystem where it's not clear where you go to get access to all the technologies you require to package a photonic device, whether for medical systems or for telecommunications. There's barriers to user access. So even if you know where to go, it's sometimes hard to actually engage and start a project. If you're an SME with a new biosensor, how you actually engage a company to develop a packaging solution around that, it's often not easy. And there's really a lack of standards. So again, when photonic integrated circuits are designed by some SMEs or some organizations, and there's no standard practices in play, which means you actually have to do fully customized packaging solutions. These are really expensive and really time consuming. From a technology point of view, thermal sensitivity and hybrid integration are two significant challenges in photonic packaging. They really add to the cost, but one of the main drivers of the cost is actually the alignment tolerances. So you're typically aligning optical fibers to biopics, and where you need alignment tolerances of sub-micron to actually get good light coupling to and from your chip. And this is really expensive if we compare it to electrical packaging, which is kind of far more developed in that regard because the alignment tolerances are significantly easier. Again, these challenges form a significant bottleneck in the packaging of PICs. So again, there's lots of great PICs being produced, lots of excellent research being done, but not enough of them are actually going through into packaged devices that can actually be tested and actually used in photonic systems. And this is where the Pixapp pilot line comes in. So Pixapp is the world's first open access PIC assembly and packaging pilot line. So we're a distributed network of photonic companies around Europe, managed and directed by the Photonic Packaging Group here at Tyndall. And we have three main objectives. So number one, we have to be a single point of contact for all PIC packaging across Europe and the world. Two, we have to offer generic packaging solutions for a wide variety of PICs, whether it's a biopics for virus detection, an optical transceiver, or optical fiber sensor, for instance. And three, we have to create a credible strategy for future full-scale PIC manufacturing. So if a customer comes to the Pixapp gateway and they want to scale photonic packaging product to large volumes, Pixapp is there to do the prototype development, medium-scale development, and then also show that there's a credible route to future full-scale manufacturing of that particular PIC-based product. So again, as I mentioned earlier, so Pixapp is a distributed network of packaging partners, of photonic partners around Europe, and the goal is to cover the full packaging supply chain. So this includes companies involved in standardization, and companies involved in actually making the software that you actually design PICs with, like Synopsys, foundries, technology partners, packaging assembly companies that are going to be used to scale up packaging processes to large volumes, and as well as equipment companies, which are key as we start looking towards large volume photonic packaging of biosensors, telecommunication modules, and how you actually design the packaging equipment becomes critical here to actually reduce costs and increase the throughput. And all these organizations come together under the umbrella of Pixapp to really create optimized PIC packaging for Europe and the world. So in light of what's happening in the world right now with COVID-19, again, one of the partners, which I guess is in the news a lot, is actually Randox. So Randox are a biosensor company in the north of Ireland. They're one of the largest in vitro diagnostic companies in the world. They're one of the main producers of the actual biosensors for actually detecting COVID-19. And so they're working with us in Pixapp to help develop our own biosensor application, or biosensor demonstrator within Pixapp that I'll talk about a little bit later. Now, I guess to summarize what Pixapp is really here to do, we're here to offer customized packaging solutions through standardized packaging technologies. So we want to create standardized packaging processes that can be used for a wide variety of different applications. So again, a user can pick and choose from certain processes, know they're scalable, know how much they cost, know where you can get it done, and then combine these in unique ways to actually make their own particular photonic package. And we call these processes our packaging building blocks. So optically, this would include how you attach fibers to edge couplers on a PIC, grating couplers, laser welding, how you do PIC-to-PIC coupling or PIC-to-PIC coupling, for instance. Electrically, it's standardizing DC RF wire bonding, hybrid integration of electrical ICs onto PICs or onto other ICs, and really how you design RF and DC packages as a whole. Mechanically, it's looking at how you integrate text, how you do thermistor integration, and design custom heat spreaders. And again, that's what's our most interest for today. It will be on our sensing building blocks. This includes microfluidic integration. So again, how you get actually microfluidics onto the surface of chips so that they can interact with the actual device there, as well as developing free space optical connections that I'll touch on a little bit later. But again, for disposable biosensors, you really want to get light to and from a chip as quickly as possible, and you don't want to have to rely on actually gluing optical fibers in place onto a PIC if the sensor is going to be disposable in any case. So to actually develop these building blocks, what we actually did a couple of years ago was actually designed a series of reference PICs based on the main photonic platforms across Europe. So we got silicon PICs from IMEC, silicon nitride from LioniX, indium phosphide from Smart TUV, silicon nitride from IMEC, and indium phosphide from HHI. And on these reference PICs, we essentially replicated the same electrical, optical, thermal, and mechanical interfaces. And then we use these test structures to actually develop our packaging processes like fiber-attached edge couplers, for instance, optimize them, show how scalable they are, and actually determine what kind of the minimum cost we can do for each particular process. Now, these reference PICs have been designed, fabricated, and validated. So again, here you can see some of our indium phosphide chips where you can see there's edge coupler. Again, there's similar repeated structures on each of these chips, like edge couplers, RF bond pads, structures for flip chip bonding, DC bond pads, etc. For our silicon-based chips, you can see on the left we've got SOI from IMEC. We've got silicon nitride from LioniX. So again, this is at 1550, not for the visible wavelengths. And then we've got silicon nitride from IMEC from the Pix for Life pilot line as well. And again, this would be for life science applications. Again, the types of building blocks we're actually developing as part of Pixapp includes edge coupling of fiber arrays to silicon, silicon nitride, indium phosphide, or also optical interposers for pitch reduction, for mode reduction, and also doing something similar for grating coupling, where we're doing high-speed fiber array attached to grating couplers on SOI and silicon nitride, and really trying to optimize the overall process, optimize the tooling, and make these processes absolutely as standard as they can be to make packaging cheaper for any prospective customers to Pixapp. Electrically, we're looking at single die-level flip chip bonding of electrical ICs onto PICs on the different platforms, as well as looking at wafer scale assembly. So again, how can we scale these processes up to large volume using laser-assisted reflow and wafer-level assembly processes to do multiple dies in parallel? Another large aspect of what we're doing is kind of wire bond standardization. So when you're doing RF or electrical packaging, how should you define your what metals do you use for your RF or your DC bond pads? How strong are these bonds? How reliable? What metallization should you pick? And then tied into that is actually interposer standardization, which is becoming more popular. So as PICs are becoming more and more complicated, designers are squeezing more and more functionality into them. You need more and more DC or RF contact pads. So how can we start to standardize electrical interposers, start to route these electrical connections out to PCBs where they can be more easily tested or interfaced with subsystems or larger systems themselves? Now, the benefit of having these packaging building blocks validated is that essentially we can create a menu of packaging processes. A customer can come to the Pixapp gateway and essentially pick and choose in this menu of different options, and then we can build a customized photonic package around those processes. And the customer knows exactly how scalable they will be and will have a really good idea of the overall cost of a project if they're looking for small, medium, or large scale volume. So for instance, a customer could pick fiber to grating coupling with a flip chip bonding with DC PCBs and microfluidics. Well, you can discuss that project with the team here at Tyndall in the Pixapp Gateway office. We can put you in touch with our partners within Pixapp who are the world leading experts in those particular processes, and we can really kick off a project then around those particular processes to whatever scale you actually need. Now, to show these building blocks can actually be used in interesting ways, so rather than just having them as a menu, we really want to show that they can actually be used for particular applications. Within Pixapp, we've started to make packaging demonstrators. So this is where we're taking these packaging building blocks and we're creating demonstrators around them by combining them in unique or different ways. So we're not aiming to make the world's best optical transceiver, but we're showing how you can combine different packaging building blocks to make maybe the most efficiently packaged demonstrator you can possibly make with what's available technology-wise in Europe. So we've got a demonstrator based on indium phosphide chips where we're looking at packaging a high-speed transmitter or receiver based on indium phosphide from HHI. We've got a data communications module where we're packaging a one-chip optical transceiver using chips from IMEC. We've got an optical fiber sensor that's led by Technovus where we're using indium phosphide from Smart Photonics for an optical fiber sensor. And then of most interest with today's discussion is an optical biosensor where we're using silicon nitride chips from Pix for Life to actually make a very low-cost prototype package for an optical biosensor. And I'm going to spend a little bit more time now talking about that. Again, this biosensor is based on IMEX silicon nitride platform, so again from Pix for Life, like Inigo mentioned on the earlier talk today. And the goal is to make a proof of concept demonstrator based on one of Randox's drugs of abuse assays. So the overall goal here is to actually take a silicon nitride chip, integrate it within a polymer cartridge, and then make an external holder that can actually take that microfluidic chip and actually couple it to an optical fiber in a very efficient, low-cost way without using active alignment. So again, this should be a holder that can be reused multiple times, and you can actually interchange these cartridges for disposable biosensing. And again, the goal here is to make these sensors as cheap as possible. So we want to package those chips within the polymer cartridge, again, for less than €5 or $5 per unit, so they can be thrown away after one measurement is performed. So IMEC are leading this work package within Pixapp. And we've also got Microfluidic Chip Shop, KIT, Argotech, Randox, as I mentioned earlier, Tyndall, and we're also using chips from Pix for Life then as well. So what exactly are we trying to do within this demonstrator? Well, we're taking a microfluidic cartridge, a microfluidic chip shop design. So again, this can be made in bulk. It's very precise using precision molding. And in that cartridge, we can actually integrate a silicon nitride PIC. Again, the silicon nitride PIC has already been activated. We now have a packaging process where we can integrate that silicon PIC within the polymer cartridge without impacting its biofunctionalisation. On that cartridge, we actually have a microfluidic channel. So microfluid can actually be brought over the surface area of the PIC. And then we also have exposed regions for the optical IOs as well as the electrical IOs. So again, here you actually have a space in the cartridge where you can actually interface an optical fiber to put light in and out of the chip. And likewise for electrical IOs, if for some reason a customer requires electrical connectivity on their chip as well. So this particular cartridge goes into a custom designed mechanical holder where it can actually be aligned to an optical fiber array within the assembly itself. And the overall goal here is that we want to make this passively aligned. So you don't have to actually actively align that individual cartridge each time. We've got a microfluidic channel that gets brought in over and gets connected to the microfluidic cartridge so the fluid can actually flow onto the chip. We have the optical IOs through an optical fiber that's actually separate from the PIC that I'll talk about a little bit later. And then we also have this arm that can actually tilt down and make contact with the actual electrical connections on the cartridge and on the PIC itself. Now, the standard way of actually forming an optical connection to a photonic integrated circuit is you take an optical fiber and you align it to the grating couplers or the edge couplers and you glue it in place. But for an optical biosensor, that's not something we want to do. It's a relatively slow process. And also if the chip is supposed to be disposable, we don't want to be throwing away our optical fiber each time we're doing a new measurement. That adds to the cost, and we want to keep the cost as low as possible. So what we're using here is actually micro-optics. So again, we've got micro-optics actually on the fiber array and also on the chip itself. These create expanded beams. So by having two expanded beams on both the fiber and on the chip, we actually greatly relax the alignment tolerances. So by using micro-optics rather than doing standard butt coupling, we relax the alignment tolerances, and we can now start to use the inherent mechanical alignment tolerances or alignment features to actually align a fiber relative to a chip and actually still maintain good coupling, which we wouldn't be able to do without this micro-optics in place. So how are we accomplishing this within Pixapp in our biosensor demonstrator? Well, we take the microfluidic cartridge. First of all, we start with a silicon nitride PIC that's already been activated. Again, part of LioniX have a process for actually integrating microlenses on a wafer level process on the surface of the silicon nitride PICs. We take that silicon nitride PIC with the microlenses already in place, and we actually assemble it into the microfluidic cartridge using our process that does not impact the biofunctionalisation. Once the chip is actually in the cartridge, the grating couplers with the microlenses directly on top are exposed, as you can see in the figure on the bottom right. And we also have the bond pads exposed as well if electrical connections are required. That cartridge can then slide into the mechanical holder we've designed, where it can interface with the optical fiber array that's aligned to it. The optical fiber array has 3D printed lenses on it, which again creates expanded beams. So now we've got an expanded beam coming from the optical fiber array, and also an expanded array coming from the microlenses directly on the chip surface itself over the grating couplers. And this really gives us this passive alignment that we actually need to make this a very quick and efficient coupling of microfluidic cartridge to the actual mechanical holder itself. So here you can actually see a side profile view of the system. So again, on the figure on the top left, we actually have the fiber array with the 3D printed lenses in place. And then we've got the bottom surface of the PIC with the lift lenses, so that microlens array directly printed on top of that particular chip. And with this system in place, we've actually greatly relaxed the inherent or the overall alignment tolerances of the entire system. So in the axial direction, so again, the direction to or from the actual chip, if you start to move the fiber array closer or away from the chip, we've actually relaxed the alignment tolerances by over 2 orders of magnitude. So again, rather than needing the optical fiber array to be a couple of maybe 1 or 2 microns away from the grating couplers on the chip. We've now actually increased that to several millimeters. So again, your fiber array can now be millimeters away from the chip, again, allowing this pluggable connection. And pretty most critically, we've actually relaxed the radial alignment tolerances. So this is where you misalign the fiber in X and Y relative to your actual pick itself. So again, usually if you're misaligned by about 5 microns, as you can see in the figure on the right, you get a 10 dB drop off in power. Where we're using this micro optic solution, we've actually greatly relaxed that. Where now if you're misaligned by 5 microns, you're only seeing a drop off of maybe 1 or 2B. And this really stretches out to about 30 or 40 microns, where now you can be significantly misaligned with your fiber respect to your pick, and you're still getting actually quite good coupling to and from the device itself. And so where are we right now with Pixapp in this biosensor? Well, we've already just developed a full package assembly flow that's compatible with biosensing. So again, what's critical here is that the package assembly flow we've developed does not actually impact the biofunctionalisation of the chip. So again, it's really suitable for actually packaging. We've actually already done the first demonstration of the biosensing capabilities of a fully assembled cartridge that you can see in the bottom left. And again, we've already shown that a CRP antigen can be bound to the silicon nitride waveguide, and we can actually measure a refractive index change. So again, I'm not an expert in this particular test, so this work has been led by UGent. And again, if you want more information on that, I can put you in touch with Maria Benitez, who's the work package leader for this particular activity on the testing side. So again, what's next for Pixapp? Well, right now we're currently working on optimizing the biosensor assembly flow to make sure each particular process or each particular step in the overall process for assembling this biosensor is as optimized as possible. And the next step then is to actually start to assemble more of these demonstrators where we can start to show SMEs, organizations, how we can actually do very low-cost, scalable photonic packaging of optical biosensors. I guess with virus detection in mind now, which this is so much in the news and so many researchers are going to be looking at kind of very low-cost, quick ways of actually testing for viruses like COVID-19. And our ultimate goal is to provide access to users all around the world to this technology and really speed up the overall development of optical biosensors. So again, really the goal of Pixapp as a pilot line is to bridge the gap between low volume prototyping for researchers and large scale manufacturing. So we're going to bridge that gap between the research that's being done in labs all around the world and how they can actually scale that prototyping, piloting, and ultimately large scale manufacturing. So in conclusion, so Pixapp is the world's first open access packaging pilot line. We're a single point of contact for a wide variety of packaging services, from telecommunications right through to biosensing packaging. We've got open access packaging processes that are scalable. We know the costs, we know what the capacity is, and right now we're starting to offer scalable biosensor packaging solutions. So thank you very much. That's all from me.
Thank you very much, Padraic, for this presentation. Okay, so now let's go for the questions. So yes, Jörg from Nanoscribe has a question, and well, it also combines with the question that I have. So Jörg say, what are the challenges in the final packaging and combination of the chips with laser sources? Yes, that well, you were talking about the micro lenses, no? How to use the micro lenses. Do you think that these micro lenses are going to offer the enough tolerance so the chip can be disposable, so we can put in, we can take out? What do you think?
Yeah, I think that's really what we're working on right now in Tyndall and Pixapp. So again, these micro lenses, we've already shown that they can really relax the optical alignment tolerances or the mechanical alignment tolerances involved. So again, in the lab, we've already shown that we can actually misalign the fiber 30, 40 microns and still get reasonably good coupling to and from the chip. So I really think these micro lens systems are really the way forward, where we're going to be making pluggable connections to and from chips. And we also have other demonstrators within Pixapp where we've put these micro lenses onto MTP connectors and actually made pluggable optical connections to and from SOI chips. And it works very, very effectively. So I think we're going to be seeing more of this in the future, definitely.
Okay, it looks promising. And what about the plans for automation and ramping up of the volumes? Inside for these packaging processes?
Yeah, so that's something we're really looking at. So I think one of the keys here is that we're working with Photonics. So Photonics are a very big partner with us in Pixapp. They're one of the world's largest photonic packaging equipment companies. So they're really here to make sure that we can scale these packaging processes up to large volumes. And that's their main role. So it's making sure that the processes we develop are scalable with our packaging partners. So that will be Fix, Cordon, Technobis, and Architect. And then working with Photonics and those partners, making sure that we can scale all these processes up to very, very large volumes as required. And really key to that is the packaging equipment, making sure we've got a good process that's compatible with the equipment and optimizing the equipment then as well for really large scale, low cost, high throughput packaging.
And for going on with all these, I guess standardization is key, right?
Yeah, I think that's ultimately how we're going to get towards those low value or those very high volumes. It's starting to standardize picks so that we can start to use our standard packaging processes, start to use standard packaging housings like the microfluidic cartridge that I showed earlier. And I think that's really one of the main ways we're going to reach these high volume applications.
Okay, so thank you very much, Padraic, for answering the questions and for the presentation. Now maybe we can go to a final round of questions. We can check out the questions from our audience. So if you want, you can unmute yourself. So yes, there is here a question that probably is for Arne. If apply a whole blood sample, would you think red blood cells will give a specific answer? And this question is from Huyu Lu from Tyndall National Institute.
Yeah, so the question with blood is indeed that's a difficult one to measure. I always understand from the people working with these kind of samples. So what you will have to do some tricks there indeed to separate that on the chip. But also there, your chemistry or your microfluidics can be developed such that you can separate that already on the chip. But that's indeed, it's a valid question that red blood cells can immediately ruin up your measurement indeed. So you have to separate that from the components you want to measure.
Okay, Arne, probably I have another question for you. What is the lifetime of these sensors? Do we need any specific storage? Yes, Tarun Narayan from Tyndall National Institute. They are asking, well, he is asking about the storage of the chips once after drying.
Yeah, so in principle, what you need to do is the functional layers you can save for a long time if you store them indeed either in sealed packages or under nitrogen environment. So ideally what you do in these kind of samples, if you have the chips which are bio-coated, you put them into some kind of a blister pack where you take them out and at the moment you use them, they're open to air and to the rest of the environment. So at the moment you start putting them into boxes, like in the box where you store wafers or chips, where there are weakeners in the box that also end up in your sample, that will immediately have an influence on the wetting of your sample, etc. So it's indeed a valid question. You should take into account the moment you want to make it into a sensing product, take into account that you store them in the right way before use.
Sure. Okay, and a more wide question, probably for Inigo, why not? Are those sensors used widely? If not, why? What is the bottleneck? So, Inigo, what do you think is the bottleneck? Why we don't have sensors, this kind of photonic sensors everywhere?
Yeah, so again, I'm not an expert in biophotonic sensing. We are more focusing on the photonic circuits, but I can tell you that photonic circuits up to now have not been used, not only in biophotonic sensing, but in other markets, because of mainly two reasons. First of all, it's not the availability of open access platforms or foundries that were offering the fabrication of these photonic circuits in a mature and scalable way. And second, because of the availability of the different tools that support not only the fabrication, but everything around it, like design, like testing, like packaging. So what has been changed since around 2016, more or less, is that there was a big market making use of these photonic circuits, which was telecom and datacom transceivers, so communication devices. And big corporations were investing heavily on that. Big foundries are investing also heavily on that. There is a huge boom on the technology. So now actually we are seeing many other companies and markets and applications making use of these photonic circuits, but not only for telecom and datacom, but also many other markets as well. And biophotonics is one of them. So we are actually now starting to see the mass spread use of these photonic circuits for many other applications.
Can I add one comment to that, Inigo?
Sure, of course.
Absolutely.
Because what you should pay attention to, indeed, you're completely right that that's the enabled that people can now use them. But you need multiple disciplinaries indeed in these. You need packaging, you need biochemistry, the biofunctionalisation of your layers. And all these need to work together. And that's enabled by indeed the open access and by closer collaboration of the ecosystem in the last years. That where you apply your service functionalization, how you package them afterwards, that has to go hand in hand. Otherwise, you can never make something which is packaged and works in the end. But the fact that the ecosystem is now collaborating as an ecosystem enables this indeed.
Yeah, absolutely. This is actually what we have been achieving in the last 4 years with Pix for Life. Not only providing access to the manufacturing, but everything around it. So people are not out in the blue there, and they actually have all the support from initial concept, engineering, design, fabrication, testing, packaging, etc. Indeed.
Okay, Inigo, I think that I have another question for you. Why did you choose the silicon nitride platform as a detection platform from CINI, from Tyndall Institute?
That's a good question. So, as I said, there are many photonic integration platforms nowadays for photonic integrated circuits. So there is the well-known silicon photonics, there is 3,5 materials like indium phosphide, silicon nitride, even silica or silicon dioxide. But the two main ones that are being used in telecom, like silicon photonics and indium phosphide, they are not transparent below around 1,000, 1,100 nanometers. So if you want to work for most of the biophotonic processes in the visible wavelength range, then you really need to work with material platforms like silicon nitride or silicon dioxide that are transparent in these wavelengths. And between these two, silicon nitride and silicon dioxide, silicon nitride is much more compact. So it allows you to put much more functionalities and components in the circuit, and also reduce the cost because you can fit many more circuits in a wafer.
Okay, thank you. And next question, Padraic, I think you can see the question, is from Jörg Smolenski from Nanoscribe. So Jörg is challenging Padraic. In biosensor packaging, the 3D printing of the lenses seems to be key for the success. How do you see the transfer of view to use the two-photon polymerization technology for mass production? What are the open challenges you are facing? What are, if you are looking for other technologies to replace this?
Yeah, so I think the 3D printed lens is actually working quite well for us right now. So again, it's quite a scalable technology. So again, Vanguard, who are one of our partners in Pixapp, are selling machines that you can actually do this at large scale volume. And we could also use 3D or also use micro lens arrays that are glued onto the PIC rather than 3D printed lenses. But again, right now, I think for the biosensor demonstrator we're using here, we really wanted to demonstrate how these 3D printed lenses could be used in such an environment and show that they can be scalable as well. I think we are always looking at different technologies, and maybe the 3D printed lenses are more suitable for some of our telecommunications modules rather than our biosensor, but it is quite a scalable technology we found so far.
Okay, and maybe now I would like to go for a more general question. So, we are now all experiencing this coronavirus situation. How do you think it's going to impact the healthcare industry? Is for you, Padraic, if you want.
I think it's going to have a huge impact. So I think, there's going to be a huge investment now in what we're in bioscience and biosensors or in healthcare in general. I think it's really up to us now as researchers in photonics in these pilot lines to actually kind of come up with solutions and actually show that we can actually start to kind of have a benefit in the medical sector and in the healthcare sector.
Okay. Arne, Inigo, do you want to add something to this?
Well, the community now starts to see the need for high volume testing. So the critical issue, of course, what you see around the world is the lack of test, the time it takes to test. The more you can test, the quicker you can try to, I don't say solve it, but at least control things or adjust measures. So there is a need for a cost-effective, quick testing. And that's enabled by these kind of circuits.
Mm-hmm. I guess that large volume is key here because at least for this crisis, millions of sensors will be needed.
Imagine you can test every passenger coming from a flight from a risk country. See how quick you can control something then.
Mm-hmm. Okay, Inigo, something to add here?
No, just emphasizing the fact that indeed to be able to, to enable this kind of devices, one of the critical things in general for photonic integrated circuits is the bottlenecks you have on the testing and the packaging of the chips. So packaging, Padraic addressed this very well. on the testing of the photonic microchips, it's true that when you have hundreds or thousands of chips per wafer, in some cases, you really need to move into some kind of wafer level testing that allows you to speed up very much the testing and also screen the dies. And this is something that we have been implementing at VLC Photonics now. So moving into not only from prototyping, testing a few dies, but also testing hundreds or thousands of dies wafer level as well. So this will be critical also to enable large volumes for photonic integrated circuits.
So do you think that we are ready to take this large-scale manufacturing here in Europe? The ecosystem in Europe is ready for this? Well, I hope you will. Yeah.
Absolutely. Obviously, there are many challenges to address, but I think there are... in Europe, I think we are very strong in one thing, which is very high level of engineering and automation. And this is well proven in other projects and pilot lines. So I think that's one of the key advantages in terms of traditional outsourcing of these high volume things to Asia. So trends are changing very quickly, and I think we will be supporting that in Europe very quickly.
Okay, very good. So now maybe last question. What are the main needs for the commercialization of this kind of photonic biosensors? What do you think? What is the next step? What is needed? Money, investors, or we need to put more people to work on biofunctionalisation? What do you think? It's an open question for anybody. I don't know.
Your first two answers were correct. Or your first money and investors are where it starts with.
Okay.
What you need to do now is accelerate as the ecosystem. So in order to, the technology is there, we all show it everywhere that we have all the capabilities and everything works. And we now need to make sure that we can accelerate. And it starts with good people. So yeah, we should train more people. But in the short term, we should make sure that we bring this into the hospitals or clinics, and then into handheld or cheap systems that you can use everywhere, to be ready for also COVID-24 or 22 or whatever. This will not be the first one. It will not be the last one.
Okay, so thank you very much. If you don't have any final comment. No? Okay, so I think we can stop here. So first of all, thank you to the speakers. A very interesting talks and very interesting discussion. Also, thank you very much to all the audience. Well, I hope you enjoy it. Thank you very much for connecting. And well, just to let you know that this webinar will be online for 1 year. So if you want to watch it again, you can. You will receive a link to go. And that's it. Just a reminder that EPIC is adapting to these times, and now we are offering different online meetings. So if you are a member, go to our website and you can register. And if you are not a member, well, what are you looking for? What are you waiting for? So thank you very much, and have a nice day.
Thanks, Anna. Thanks, everyone.
For the organization.